There are a lot of old friends in this audience, some new ones too. It's a pleasure to be here. And it is a privilege to have been asked to open this conference. I thank the organizing committee for the invitation. My job is to provide a backdrop for the next day and a half. For the 20 minutes or so that I have, the title given to me, Electrochemistry, Past, Present, and Future, is comprehensive enough. By now, I'm a pretty senior figure in electrochemistry. It has been 53 years since I joined Alan Bard's laboratory as a graduate student. Maybe that span is why I'm standing here, for I have seen and experienced a lot of science over those years. But I don't go back to the beginning of the field. The science of electrochemistry is usually dated from 1780 with the work of Luigi Galvani in Bologna. You surely know of his experiments with frogs' legs, in which he discovered that muscle contraction is promoted by electricity and also by contact of the muscle tissue with two different metals. Galvani's work was followed up by Alessandro Volta in Pavia, who was especially interested in the electrical behavior of bimetallic systems. In the process of his work, Volta devised the first electrochemical power source, what we would call a battery, in 1799. It became known as the voltaic pile and rapidly became a tool of science, a reliable source of electricity in the laboratory. With the use of the voltaic pile, electrolysis of water was demonstrated in 1800, and quite a few elements were discovered or first isolated by electrochemical means before 1810. Lithium was first electrodeposited in 1821, providing the first sample of a pure element that we think about often these days. Electrochemistry yielded the first isolations of strong oxidizing and reducing agents, including fluorine, chlorine, and the alkali metals. When reagents like these became available, the synthetic range of chemistry expanded tremendously. This little story is offered here just to remind you of three things. The history of electrochemistry is long. It spans 240 years, almost matching the length of the whole story of modern chemistry. Technological applications of electrochemistry arose right away and began with batteries. We have been working on them for more than 200 years. Electrochemistry connects intimately and broadly with fundamental processes of science. This has been true in every age because electrochemistry links electrical energy with the material world, and because it focuses on a truly central chemical process, electron transfer. The operational range of electrochemical systems is breathtakingly large. To illustrate, let me quote from the coming third edition of the text Electrochemical Methods. Electrodes can be as large as several square meters or as small as a square nanometer, 10 to the minus 18 square meters. Current flow may be in the hundreds of thousands of amperes, or it may be in picoamperes. A current may be required to last for nanoseconds or for years, and the time scales of electrochemical experiments can extend from the indefinite to nanoseconds. The use of a system may involve no consumption of material, a few atoms, or massive amounts. In the upper range, for example, the industrial production of metallic aluminum is wholly accomplished in electrochemical cells. The global economy produces about 50 million metric tons annually. The U.S. share of this production, but less than 5% of the global total, still requires several percent of all U.S. electric power production. With this operational range, one has the latitude to imagine and to realize electrochemical systems big enough to support large segments of an advanced economy. Within that range, one can also deftly and delicately investigate new science. Electrochemistry has always been both a technological and a scientific domain. But it is not easy. To quote once more from the new edition of Electrochemical Methods, key events often take place in a tiny fraction of the total volume, typically at or very near metallic interfaces, perhaps only at rare active sites on surfaces. The reacting molecules or ions must be transported to the locales of reaction, and the processes of transport influence the reaction rates. Once a reaction is initiated at an electrode, it can proceed through a mechanism involving almost any kind of chemical step: proton transfer, a change in ligation, elimination, rearrangement, or even subsequent electron transfer, either at the electrode or with other molecules or ions. Reactions at electrodes involve the orbital structures of ions and molecules and the band structures of metals, semiconductors, and insulators. They depend, too, on electrostatics and thermodynamics. Among the domains of chemistry, electrochemistry offers some of the greatest challenges to effective theory and experimental examination yet. Over 2 centuries of genuine science, a strong base of theory and experimental methodology has been assembled. A robust science exists, established through 240 years of research. That is what the past has given us. But nearly all we know, what we can do experimentally and what we can treat theoretically, is the product of the last 3 or 4 decades. In the course of my career, this field has renewed itself at least 4 times, and it's poised to renew itself again. That brings us to the present. Compared to the past and the future, the present is but a moment. The outcome of the past and the starting point for the future. However, one can interpret the present in different ways depending on one's priorities and interests. For this conference, the subtitle is Addressing Societal Needs. So let me focus now on what that might mean. Through successes rooted in science over the past 200 years, nearly everyone on the globe is far healthier than their forebears, is much further from starvation, enjoys vastly greater mobility, and has unprecedented access to culture and opportunity. As a species, we have flourished. There are 8 times more of us now than in Volta's time, when global population first reached 1 billion. But without doubt, humankind confronts fearful challenges. The earth groans under the load of her human population and its ambitions. Past patterns of expending global resources, as successful as they have been toward improving people's lives, cannot underlie the future. Science helped to create the challenges of this era, and science is expected to address them. Electrochemistry can contribute centrally precisely because it links electrical energy and the material world. and because it has operational scope big enough to support meaningful industrial change. Toward the critical goal of transforming the energy economy to a sustainable basis, electrochemistry offers the most likely solutions in two areas of great importance: vehicle propulsion and power grid management. Electrification of vehicles reduces the consumption of fossil fuels and lowers the production of greenhouse gases, particulate matter, and ozone precursors. The long-term environmental benefits can be very large. In the end, success rests entirely on electrochemistry because electrochemistry furnishes the only answer to the requirement for mobile electric power. I will have more to say about this in a moment. An electric power grid must deliver power steadily and predictably. At present, the only clean, renewable, scalable electric power sources are wind and solar. Both are unpredictable and intermittent. The key to sizably greater contributions for wind and solar is to develop practical means for short-term storage of large amounts of electric power, creating the ability to bank excess local power when wind or solar is producing strongly, and to release that power to the grid in periods of local underproduction. The best answers to this need are likely to be electrochemical. These two domains are ripe for progress and present opportunities for tremendous economic and environmental impact. They merit close, sustained attention and investment. Electrochemistry might also afford other solutions for environmental challenges. Among them might be greener processes for chemical manufacturing and effective capture or even useful fixation of CO2 from waste streams. Economic contribution from electrochemistry is, however, far from being wholly defined by the challenge of climate change. Quite recent progress in electrochemical power sources has enabled the very broad and expanding success of mobile electronic devices and cordless tools. There is ample opportunity for further advances supporting new products. There is also the opportunity to improve chemical synthesis through processes that are more precise, also leading to new products. As we think about opportunity here in this picture of the present, we must not confine ourselves to visions built on current technology or even on technology at all. Electrochemistry connects electrical energy and the material world. This will always be a most important linkage for human existence. An ambitious, wise society will place a priority on learning all it can about that linkage. A serious program of research in the basic science of electrochemistry is essential to scientific leadership and, in the end, to the well-being and security of the nation. There is little doubt of fundamental discoveries that will reshape thinking, that will redefine the possible in ways that we cannot now accurately sketch. That brings us to the future. Where should we be headed? Where should we invest? Naturally, one's first reply to those questions is based on opportunities presently perceived. I just went through a set of those, which included all three technical topics to which panels are dedicated in this conference: energy storage, energy conversion, electrosynthesis. The speakers themselves will give more detailed analysis and advice than I can, but let me offer a few points. My earlier comments about automotive propulsion, power grid management, and portable power connect directly to the theme of energy storage. The prior comments were focused on the why, but not on the how or the what exactly. Let me add these points. In all three of those industrial areas, there are good batteries, but not good enough batteries. There are always demands for better economics, better performance, and better safety. Existing batteries are adequate for hybrid vehicles and for all-electric, premium-priced, medium-range passenger vehicles. They are not good enough for all-electric mass-market cars, vehicles suitable for intercity driving, or vehicles that offer the advantages of SUVs. That might be changing. There are no effective all-electric packages for heavier-duty vehicles, including long-haul transports, most construction equipment, or even pickup trucks quite yet. We in Austin, Texas are curious about all-electric pickup trucks. Fuel cells are attractive for vehicle propulsion because of the energy density that can be obtained with storable fuels, the ease of recharge, and the fact that the oxidant need not be carried on board. However, their economics are not competitive yet. Battery systems for power grid management are in the demonstration stage. Practical answers probably exist, but are not yet clearly at hand. The main issues are the enormity of the energy that must be accommodated in a practical storage system and the cycle life of the system. All applications of electric power sources call for research on new ideas for batteries and fuel cells with regard to both composition and design, kinetics of critical processes, and lifetime limiting processes in cells and their packaging. Let us turn now to the themes of energy conversion and electrosynthesis, each motivating one of the panels in this conference. In both areas, progress hinges on better understanding of complex electrode reactions. Electrocatalysis remains important. We need to know all we can about the details of electrode reactions of key small molecules, H2, O2, CO2, CO, N2, NH3, CH4, methanol, especially at electrocatalytic interfaces. Because these molecules and their reactions have been examined for a long time, new work needs new approaches, offering new insight. It has been long understood that large scientific and technological payoffs could stem from advances. In fact, payoffs have come. Much more potential remains. The blossoming of fresh interest in electrosynthesis also creates a value in greater mechanistic knowledge of electrode reactions, especially of those that can lead to synthetic precision. Among the most promising new directions for electrochemistry, indeed a likely basis for the next reinvention of the field, is the ability to explore events at atomic scale electrodes. Impressive recent work has shown that one can carry out catalytic electrochemistry at a single atom or at assemblies of a few atoms of platinum on a non-catalytic surface. Experimentation in this genre could lead to very significant new understanding of catalytic processes and perhaps in other important scientific areas as well. Let me close with a wish for a wise humility as we think about research in the years ahead. All of us here know the wry dictum credited to Niels Bohr: prediction is very difficult, especially about the future. It's a warning about having too much confidence in one's assessment of the future. Things will change. The possible will not be limited, even 5 years from now, in some way that applies now. Opportunity will be transformed. Some paths now appraised as very attractive will not pan out. Other opportunities now discounted or even unseen will emerge. We have all witnessed such things before, and we can be confident that we will see them again. It is only sensible to invest in the opportunities that we perceive now, especially when they seem to connect with the fearsome problems that our society and all others face. But let us also be honest with ourselves. What we already know and can refine will not be enough to solve those problems. New discoveries will be required. We cannot know of their nature at this point, and they cannot be scheduled. Thus, it is more than wise. It is an essential element of policy to maintain a vigorous, broad-based program of fundamental research in electrochemistry. We must keep learning about how and why reactions happen at electrodes and how we can control events still more deftly and with greater sophistication. This is how we buy a piece of the yet unknowable future. To the generations who follow and to ourselves, we owe a faithful, comprehensive effort. Thank you for taking the time to listen. What do you want me to do now?
Are there any questions?
That's good. Thank you. All right. You need a microphone, I guess.
Since nobody's asking anything, let me ask a question. So, in the three areas that you pointed out as the present and also part of the future, you did not allude to biochemistry and bioelectrochemistry.
Well, I think I'm trying to capture the whole sphere, of course. So I commented on reactions. Of course, the scope of reactions is very broad. One person may be interested in the reactions that are relevant inside a battery, and another person may be interested in bioelectrochemical processes. Another may be interested in synthetic precision. Those are all really different areas. But we need to know more about how reactions happen. We aren't going to learn all of that in one study. It's a tremendous scope. And so I think I'll let the speakers talk more particularly. I was trying to set a more general basis for this discussion that's about to occur. Back here?
Yeah, hi. I'm sorry.
Oh, Deborah. If you're standing at the microphone, you might as well talk, Deborah.
I may as well, although
Sorry.
I may not need a microphone.
How are you?
Larry, in addition to the perpetually awaited third edition of electrochemical methods, you've also addressed a lot with respect to educating the scientists of the future. And as somebody who hires graduate students, postdocs who do electrochemistry, I and others probably have their own ideas about what would be better educational foundation for the electrochemists of the future. Would you care to discuss a little bit about that?
I will tell you that I think the educational foundation is changing. And in fact, I mean, as we're working on the third edition of electrochemical methods, we are changing the assumptions made about that book, and that illustrates, I think, some of the things you're raising. When that book was first written back in 1980, it was essentially written for graduate students in chemistry and practitioners in the field, all of whom had come through, you could assume, had come through a classic chemical undergraduate education, including the parts of physical chemistry that are highly relevant to electrochemistry. Now you can't assume that, even about chemistry graduate students, because the nature of chemistry undergraduate education has changed. But more than that, many people have come into the electrochemical field from other types of educational backgrounds. Many have come in from engineering, many have come in from a life sciences background or a materials background. So what we're trying to do with that book is to make it less assuming of a particular form of preparation. And I think as we start to educate electrochemistry and start to receive people into the field, we have to be receptive to people who come from different backgrounds. Now, what they need to know going forward is probably a question you're asking more about.
The scope of the background. For instance, I'd rather teach an electrochemist material science or nanoscience than to teach anybody else electrochemistry, because it is rooted in the arcanity of 200 plus years ago. So I've always found it easier to bring an electrochemist to widen their scope than to bring in other areas to really do first-rate electrochemistry.
Well, I think that those are relevant comments, but there are large numbers of people coming with different kinds of backgrounds. We're trying to put them on the same page. But I think that there is a panel that is going to talk about some of this. I'll let them do it. I'm historic. So I'm not the person to tell you how to do the future. That's what this group here is about.
But you still know first-rate electrochemical education.
We had a question right here.
That was the same question, the curriculum for the scientists of the future based on the great vision you laid out. So
Okay, thank you. And right here.
I really enjoyed your remarks today. I don't wish to put you on the spot, but you mentioned the field has been reborn at least 4 times in your vision. Would you mind to recount one of those times when it seemed like electrochemistry was trailing down, but then some new breakthrough reinvigorated the field? Do you feel like
Yeah, I would associate them with. This is my reading of it, but I would tell you, I think that the revolution in instrumentation and theory that occurred in the 1960s, roughly, would have been one of those. I think the advent of spectroelectrochemical methods, the coupling of spectroscopy to electrochemical research, would be another one. The realization that an electrode is a chemical entity and can be modified and be a reagent was much more amplified by that modified electrodes wave, and then I would say the advent of ultramicroelectrodes, I think, has brought a lot of new techniques and capabilities into the field. Those 4 things would be the 4 revolutions or the 4 renewals that I was thinking about. I mean, people who come from different backgrounds might look at it a little differently, but that's the way I look at it. Okay, that's probably enough from me. Thank you all.